last year. I'm just going to turn it over to Brad and let him run. I talked to you last year about putting our development system on a coal fire core, IP core that was instantiated on an FPGA. And Brad came to me a few months ago and said he wanted to do his fourth core with our SwiftX put on it, so that cut out that intermediate layer of the cold fire with the fourth virtual machine put on top of it. So now we're running directly on a full CPU. So I gave Brad a SwiftX, off he went, and here's the result. This is a work in progress. We're not quite ready to release this, but it's quite far along. So here's Brad Eckert to talk about that.
Okay, hi. My name is Brad Eckert. I've been writing fourths for a few years now. Well, more than 15 actually, but my usual approach is to write it and give it away, post it on the internet or something. The last fourth I wrote was for my own processor, which was based. It was for a project that's still ongoing, but my approach to this project was to write a simulator that executed a bytecode virtual machine, and then eventually I decided to port this bytecode virtual machine to an FPGA, and eventually I got tired of various difficulties with that, and that's where the new CPU design came from that I proposed to Leon. I came up with that idea this year. Over the last year, I've been consulting with the guys at NXP Semiconductors. They have a high-speed interface group that develops SoC, systems on a chip. So I learned a lot of things about hardware design from those guys, about ASICs, and then that made me really want to change my design around. And also I started thinking about, well, what if I had to teach, my fourth development system to somebody else, It would make better sense if I took a stable, well-proven, well-polished fourth and ported it to my chip. So this is the result of that whole effort. So my rationale behind this thing was basically to ride, the Moore's Law wave. This year, for example, Xilinx is shipping 45 nanometer FPGAs, and next year they'll be shipping 28 nanometer parts. And each, they keep going down. They, doing stuff you never thought that was possible. They just they come out with these new process nodes, and of course, if you get to design your own CPU and your own fourth, well, they're pretty much geared to each other. And if you have control over the hardware, you get rid of end-of-life issues. So today I'm going to show you a test setup that I put on the Brevia board. The Brevia board has some neat, some external RAM and stuff. I'm not using that. I'm just using the FPGA. And Dr. Ting explained the Brevia board too. This morning, first thing. So it's got 8 LEDs and switches. I am going to launch. Okay. SwiftForth. Okay, here I just built the kernel, which contains multitasker and all your basic fourth words. And it's really not that big because, well, I'll get into the compactness of the code later. Mostly it's because the instructions are either 8 or 16-bit, and a lot of your calls can have 8-bit displacement, so it's at 8, so you can have 16-bit calls, and that's pretty compact. If I connect to this guy, okay, that took about maybe a second or two. There's a 10K byte a chunk of code memory on the brevier board that I had to reload because the image that's in there doesn't quite match the stuff I compiled right here. And I'll just do something quick. That came from the that came from the target board. It just dumped that out through the serial port. Now, if I want to turn on, I'll just turn on one of the LEDs. Okay, that one just came on. You see a blinking LED. I'll show you the source code for that. There's a task that blinks that LED, and that's open right here. There's our blinker. Just has a little background task here, and it just keeps on, toggling the LED. And there's some code up here that defines where the LED. LED 0 store is the first thing up here. Okay, well, I don't want to get into cross-compiler stuff right now. I'll just continue with the slides. Here's my test setup. Most of it is just plain generic VHDL, except for the code space up in the corner. I use the dual port RAM for that, and you can't really express that in standard VHDL. But it's really pretty simple to implement using the Lattice tools or whatever FPGA vendor. They have things for that because it's a popular thing to do. So I tried fitting the design into a few different FPGAs. And I also looked up the costs of the FPGAs on the internet, like places like DigiKey, and those are the prices. So the logic cost is, these days is pretty reasonable. Usually when I pick parts from DigiKey and then I give the production guys the cost, the high volume is usually a third of what you pay for small parts on DigiKey. And then in the future, the costs will keep coming down. Like most of the designs we've seen here, most typical FPGA CPUs, in the low-cost parts, you might hit 50 megahertz. And you could probably go faster with floor planning or something. But just taking the design out of the box, pushing a button, waiting 5 minutes or something for it to do its synthesis and place and route, you end up with a 50 megahertz, timing pretty easily. Without going back to the setup slide, there's a port for adding a custom coprocessor. On the demo board, I put in a little math processor that does divide and square root and multiply. Uses the hard multiplier. So basically, I tried to make it reasonably compatible with FPGA and ASIC design flows. There, you kind of have, I mean, each design flow kind of has its own strengths and weaknesses. Like, for example, if you have a lot of muxes, that's, not too good for FPGAs, but they're pretty cheap in ASICs. Now, on the other hand, FPGAs have lots of adders. I mean, it's pretty quick to implement adders in FPGAs. One of my primary goals was to make this thing a lot like the PC environment. Byte addressed, 32-bit little endian, and automatic stack spill, so that you don't have to, worry about managing the stack. The neat thing about FPGAs is your code space is right on the chip, so you don't have, so the code memory is no longer a bottleneck. So with that in mind, I decided on a 16-bit code word. Here's a really simplified block diagram of the core. There's a couple of on-chip return, stacks, and there's a group of registers. And I kind of intended these three things to be implemented in LUT RAM or distributed RAM, whatever, on the FPGAs. Usually, FPGAs will give you these RAMs pretty efficiently. And the prefetch unit kind of does a lot of the work of managing how the instructions are fetched. It'll actually look at a few bits of the instruction and decide whether it's an 8-bit instruction or whether it's a 16 or etc. Whether the instruction needs some extra data. Immediate data. I'll get into that on another slide. Here's that group of registers I mentioned before. The stack pointer and return pointer are necessary for the spill and refill, and you have A and B registers, which you use for load and store. That's kind of you might be familiar with that. If you saw Stephen Pelk's proposal for a new fourth virtual machine, where he was going with that was to make something that's more compatible with C compilers. So I already had the A, B, and SP and RP in there. I needed those. So I just kind of added the X and Y in there. X and Y also support base plus offset, where offset is an immediate number following the opcode. In SwiftX, X is used for addressing user variables. Okay, this is all the opcodes in here. So these are the opcodes that have immediate data following them. They could have 1 byte, 2 bytes, 3 bytes, or 4 bytes of assigned immediate data, and that immediate data is all collected by the prefetch unit and fed to the ALU along with the opcode to execute. So these guys all execute in one cycle, and then some of these might need 2 or 3 cycles to execute, depending on how many 16-bit chunks of data has to be gotten by the prefetch unit. And the ones with the gray background, they're all load and store. You can see that covers about half the opcode map, because there's all these different data sizes, since it's byte address, and there's also quite a few address registers. As I mentioned before, the instruction format as far as determining the data sizes pretty straightforward because the prefetch unit has to go and get immediate data and feed it to the CPU. So the instructions are in groups. I'd like to you'd probably, darn, okay, up we go. So if you do a disassembly of instructions, you'd probably you're going to see I don't know what I'm going to disassemble. Okay. Instructions are in groups so that to make them an even number of bytes long. Like here, there's padded with a no-op. This is a 16-bit immediate data. So the BB is the BSR operand, and it's got some immediate data for the branch displacement, and then just a no-op for padding. Okay, I also put an interrupt controller in this thing. And it's pretty much like the old 68,000 Codefire style thing. When an instruction is taken, it saves different things like carry and overflow onto the stack, and then it also sets the priority level to so that lower priority interrupts won't be taken until after you return from the interrupt. Instead of forcing the user to always implement I/O bits as a peripheral in data space, there's some bits that are connected right to the core, so they're basically quicker to use. Like this example shows an SPI. It's kind of not the greatest real-world example. For example, this part where you raise the clock and lower the clock, there's only 2 cycles between here, so you don't want to just raise the clock for 2 cycles and then lower it. But this executes in 1 clock, this executes in 1 clock, and so on. When you read a single bit, it returns 0 or -1. That's why the sub is there instead of add or. Bit banging SPI, right? Yeah. Yeah. SwiftX is a tethered forth. That means that all the brains, all the heavy lifting is done by the PC. There's a thin client communication thing going on, and on the target board there's actually just a small thing that gives you access to memory and such, and lets you execute words at a given address. Now here's something interesting that I did. I didn't implement the SwiftX side of it, but you can actually connect the SwiftX to an RTL simulation like ModelSim, and have and actually run an interactive session. So basically, the UART talks to the SwiftX through a couple of mailbox files, and that's okay because the files are cached by the OS. There's not a bunch of disk thrashing going on. And it's just generic VHDL. There's nothing really special going on. This is just to recap the ports that are on the CPU. At the top level, you have the XTL port. There's interrupt requests, input bits, output bits, wake up. Wake and sleep is just, you can actually shut off the CPU, and then a sleep signal comes out, and the hardware design can be set up to gate off the clock to the CPU for deep sleep mode. And then you tell wake is an incoming signal. So this is just a kind of a handshake for managing deep power down. There's just a single clock on the core, and there's a single asynchronous reset. Code and memory are different ports, but they're in the same they're in the same address space. So there's a unified address space. It's not like an 8051 where you have 2 or 3 different address spaces you got to mess with. This slide shows some sample usage of the core of the SC20. If you can see, the right side is data space, right? There's a blue address bus, and there's a red outgoing data bus that kind of goes to all your data thingies, and then you have the green input bus, which has to be muxed from all your things. On the left side, you see code ROM is a place you'd keep all your interact vectors and your kernel, and anything else in your application that has to run really fast. And your code RAM would be a place to put a place to do interactive debugging and code development. By the way, in an ASIC, ROMs are much smaller than RAMs by a factor of maybe 10 to 1. The SPI flash controller, the thing about FPGAs is a lot of times they'll boot off an SPI flash. And even if they don't, like say the flash lattice part, it's a great place. It's a great place to store large programs. I'll just hit the highlights of these slides. The interesting thing about the code ROM is that the lower 256 words are used for software interrupt vectors, so that if you have a big application running in the external flash, say, it can use software interrupts to invoke, different kernel words. And if you change the ROM, it doesn't break any apps. It keeps binary compatibility. The code RAM, as I mentioned before, it's good for developing code in, of course, interactively, and also the interrupt vector pointer can be redirected to this RAM. So instead of using the vectors at the bottom of ROM, you can use the vectors at the bottom of this space, and then that allows you to patch, well, just any ISR